So a vertical asymptote is a line, it's a vertical line. It's not actually going to be on the graph, so we have it dotted because it doesn't actually exist. It's just a boundary that your function will not cross. So your function is either going to go down to negative infinity at that point, or it's going to go up to positive infinity, depending on how the graph looks. Whether you come from the left or the right will also depend as well. So you can use all that arrow notation that we discussed in a previous video to help you with those definitions. So how do we identify them when we are given a function? So if you are given this function p of x over q of x, and they have no common factors, that's the most important thing. If they don't have any common factors that you can divide out, then all you have to do is find the zeros of the denominator. And each of those zeros will be a vertical asymptote. You could have 1, you could have 2, you could have 3, it just depends on what your denominator is. So let's go through a couple of examples and we will identify those vertical asymptotes. All right, so here's my first one. All right, so notice I'm going to factor the numerator and the denominator. So the numerator I can't do anything with, and the denominator factors to x plus 1, x minus 1. All right, so notice there's nothing that can divide out. So we're going to have two asymptotes. This will give us an asymptote of x equals -1, and this factor will give us an x asymptote of +1. If we put either of those values into the function, we will get 0 in the denominator. So very similar to your domain restrictions, right, that we've talked about earlier. So we will have two vertical asymptotes, and that will be their equations, right? Vertical lines are always x equals a number. Right, and here's the good news, is you can always check if you want to take that graph and put it into some type of graphing calculator or a graphing software package, like I always use Desmos.com. You will find that that is what the graph looks like down here in the lower right, and notice you have that vertical asymptote at 1 and another vertical asymptote at -1. The function never crosses those two lines. So it's always nice to check yourself with the graph. So feel free to use those graphing software packages or calculators to do that. All right, what about this one? All right, again, we would factor anything that we had. Now the numerator we can't factor, so that's great. Notice the denominator, you can't factor that either. There is no factoring for the sum of squares. So this cannot be factored, so nothing will divide out. And since that happens, that means we can put anything we want in the denominator, right? Notice, when is x squared plus 1 not going to be equal to 0? Well, that will happen only at imaginary numbers, right? Because you have x squared equals -1. So my only restrictions on this would be two imaginary numbers, which that's not going to affect us when we're graphing anything that's real. So this one will have no vertical asymptotes at all, because there are no real restrictions happening to our function. And if you'd like to, again, check it using a graphing software package, please feel free to do so. That is what the graph looks like, and notice no vertical asymptotes at all. So we have the correct answer. All right, then let's look at this one, x plus 1 over x squared minus 1. So x plus 1, I can't factor that, but I can factor x squared minus 1. That is x plus 1 times x minus 1. Okay, notice you will have these two domain restrictions. However, this factor will factor out, right? So this will divide out. And any time that you have a factor that will divide out, you will still have that domain restriction. So you will still have, so I'm going to put a couple of notes. You will still have that domain restriction at x equals -1, but it won't be an asymptote. What it will be is a hole. Anytime you can divide out, you create a hole in the graph. So there's going to be a hole at the point -1 comma something. We can figure that out by evaluating the graph at -1. So that's the good news. So this right here is just the function evaluated at -1. And there will be a hole in your graph. It will not exist at that point. All right, so this function will simplify down to 1 over x minus 1, which that still has a vertical asymptote, right? We'll have a vertical asymptote at x equals 1. But when we graph it, we should have a hole here. So I can plug that in and find that hole. Again, we're not going to graph it right now, so we don't have to really worry about doing that, but that's how you would find the hole. So if I go to the graph, again, you can use any graphing software package you want. notice there's going to be a hole right here at -1. Here's your vertical asymptote at 1. Here's your hole at -1. Very important that you know what the hole looks like. The nice thing is if you graph this original function and you graph this simplified version that we had, they will look almost identical except for the fact that that hole won't be there. The hole only exists for this original function. This simplified version just gives you kind of the easier version to graph it. So you can just plug in the numbers a little bit easier, but you should have a hole at -1 because of that original restriction. So just be very careful when you're looking for holes versus asymptotes. So remember, holes come when you can divide out, like I showed you. When you can divide out a factor, that's where the hole is going to come from. Anything that's left over will be a vertical asymptote. So hope that helps. Come back next time and we will talk about horizontal asymptotes. So see you then.